it's been pretty amazing to be kind of at the forefront, at the cutting edge, to see all the luminaries in the field, and you find out that these big names are just people with a lot of common interests that overlap with yours, and who will only be too happy to talk with you about them.
I'm Roth Michaels. I'm a principal software engineer at Native Instruments. And you might have heard me give other talks at CppCon in the past, claiming I worked at Isotope. A few years ago, Native Instruments, Isotope, and then the Brainworks and Plugin Alliance brands, all kind of three big players in the digital audio space, went through a merger. And so that's kind of the big theme of today's talk, is these are all 20-plus-year-old companies. And so we have experiences dealing with legacy code in one place, and then what do we do when we're pulling this all together? So for those who don't know what Native Instruments and Isotope and Brainworks are, we make hardware and software for music and audio production. So everything from mixing and mastering records, producing beats, DJ software, post-production to clean up audio for film, television, radio, and all sorts of things like this. And this picture here is showing some products existing within Apple's audio editor Logic. And this is kind of another big part of our world is, while we do make some applications, a lot of what we make are DLL plugins that run inside of somebody else's process and memory space with a bunch of other folks playing along. So that's often something that surprises people when they hear about our industry, but that's not too much of a topic that we'll get into today, but you'll see later that our kind of experience with working this way led to some of our code sharing techniques. So to finish off your Wednesday at CppCon, this is going to be a little bit light on code. There is non-zero code slides, but this is mostly story time, where we're going to kind of go through a bunch of experiences I've had trying to improve our own legacy code base on the Boston side of things at Isotope, and then 4 different strategies we've played with for how to share code with 3 giant C++ code bases that range from 20 to 25 years old. Before I get into that, this is kind of something I like to do at the beginning of all my talks, is encourage all of you to give a talk. This talk today, like I said, it's story time. It's a bunch of interesting things I've discovered and worked with, and things that worked and didn't work over the last few years. I'm sure many of you in the audience or listening online probably have interesting stories to share that have happened either in your personal experiments or work. And if you've never spoken at a conference, I encourage you to think about trying it out. There's a lot of good resources for getting feedback on your proposals. And also, if you haven't signed it, it's probably too late this year, but the lightning talks are also another great way to dip your feet into things. And just want to mention that my whole life is in legacy code. One of my first talks at CppCon was actually about getting to write new libraries. And so while we do get to write new libraries from time to time that are using the latest, greatest C++, best practices and all that, we still have lots and lots and lots of old code that we're dealing with. So I'm going to ask for a little audience participation here. Could anyone throw out, and I don't need to go to the mic, I'll repeat them, but some things that come to mind for you when you hear legacy code and what that is?
Code without tests.
Yes, code without tests. I think that's my first bullet point on the next slide. Anything else?
Built under an old standard.
Old standards.
Technical debt.
Technical debt. In production.
Monolithic.
Monolithic. Yeah, in production. I didn't thought of that one, but I like that one. As soon as it's in production, considering it legacy is good. Anyone else want to throw something in?
Code I used at the beginning of my career.
Code from the beginning of your career. No documentation. I think a lot of new code has that, so maybe it comes out of the box legacy also. So these are some of the things that were on my list. Certainly not exhaustive, but inspired some of the things we'll talk about. Yeah, Sid, no tests. Not always, but usually there's lots and lots and lots of code. Maybe you don't even use it anymore, all of it, you don't know. Likely very old. Likely the authors might not be around anymore, so you might have huge libraries in your code base that, hey, they work, we know how to use them, but who wrote that code, we don't know about. When you see the to-do comment from the founding CTO written 18 years ago, you have no idea, does this actually matter? Or was this just a dream of his and no one cares about this anymore? Someone mentioned standards, we're getting an old standard. I think maybe even trickier one is a code base that has been across many standards. So I think at Isotope in Boston, well before I joined, I think they were pre-C98 for a little bit, and then went through all of the transitions. So we definitely have many eras of code things in our code base. Like one example is we have a capital const expr macro, because I think one compiler had it and one didn't, and so we did that. New and old styles. And I put that twice. I think the second new and old is supposed to mean like programming paradigms. Bad decisions from the past that might have actually made sense 20 years ago with the way the business and the software went then, but as things grown, they realized, oh wow, we've got performance problems due to this. And not always, but possibly written by a less skilled engineering organization. If your company's legacy code came from being a startup, they might have been fresh college grads that found this company and are just very new to C++. And over the years, as they build up the business, can hire more and more experienced people, the knowledge and skill level of the C++ at the company can rise, but that might mean you see some pretty weird stuff in your old code. So I just want to put an aside on this. This is something a colleague told me about on Monday, and since my talk got moved up from Friday, I didn't have a chance to actually try this tool out, but he recommended this book to me, Your Code is a Crime Scene, for like understanding how to look at legacy code. But there's a cool tool that comes with it called CodeMat that will apparently tell you things about your code base, looking at the Git history, like how much your code is written by people that don't work at the company anymore. Or every time you change this class, you also change this function over here. Every time that happens. And then you can look at that and say, like, was that a good thing? Are these related for business reasons? Or is it just tight coupling that shouldn't exist? So I recommend you check out that tool. I haven't had a chance yet, but it sounds cool. And just a disclaimer, a few times throughout this talk, I might mention like doing things for business reasons when we make our engineering trade-off. And obviously not everyone might be in a business context, might be working on open source. But really what I mean is making engineering decisions that are gonna benefit for the sake of you delivering value to your users as quickly as possible and being pragmatic about that so you're not focused just on making the prettiest code base you can make. And another aspect of it, I mentioned, lots and lots of code. This is a slide I made for a presentation a number of years ago about just the Boston isotope side of the code base. And we see we're dealing with millions of lines of first-party code that exists across all of our modern and legacy product lines. And now that we're 3 merged companies, this could easily be a few more millions of lines of code. So before we go into talking about like some good strategies for dealing with legacy code, I want to tell you a cautionary tale of something I saw recently with some Python libraries and adding linting, type checking, and unit tests. So internally, we wanted to update how we're dealing with our Python tooling. We wanted to use poetry versus setup py. If you don't know what this means, it doesn't matter. PyProject TOML files for restructuring stuff. But our default template for best practice for a new Python library, we were using that to roll out to old libraries. And so this all of a sudden activated new linters or new type checking. And actually pass those linters and type checking, you would have to change the code. And some of these libraries are working fine on their own, but introducing these new linters, changing code, I'd say half the time this modernization was done, there was an unknown breaking bug that was introduced when these code changes happened. A similar one is I had a test automation team that wanted to have a goal of increasing test coverage on their tools. But instead of just having a mandate of like, okay, we're gonna have tests on all new code, they actually went back to a bunch of easy small libraries and added unit tests there. But those libraries are like single purpose Unix style tools that probably are never gonna get another feature again. They work, we might not ever have a bug fix. So why did you put that effort into making those changes? Especially if you had to refactor to make something more testable. But if you actually, that refactor normally means you didn't change behavior, and that's actually very tricky to also do when you're testing. So if you need to add more tests for stuff that doesn't have it, it's probably good to think about other higher level testing, like acceptance testing, to make sure you have some coverage, because adding tests to untested code doesn't necessarily make that code right if you have to change something. Another thing is, this is maybe putting a lot of effort into something that didn't matter, putting testing on code you're not changing, because on Ben Dean and Matt Godbold's podcast, I forget which episode, but one of them mentioned some thesis that over, I forget what percent, but they said, over 5 years, a whole bunch of your code base is probably gonna get touched or rewritten. And those are the parts you might wanna care about modernizing and improving. But the parts that are down deep in the guts that do their thing, hopefully it's correct. If no one's touching it, what is that extra test coverage we're gonna give you? And the reason I have this cautionary tale about the that Python tooling refactoring is adopting those linters and type checkers required actually changing the code, which could lead to some mistakes. And so I'll play one of my favorite quotes from 2001 I often share with my colleagues on this topic.
I hope the two of you are not concerned about this.
No, I'm not, Al.
Are you quite sure?
Yeah, I'd like to ask you a question, though.
Of course.
How would you account for this discrepancy between you and the Twin 9000?
Well, I don't think there is any question about it. It can only be attributable to human error. This sort of thing has cropped up before, and it has always been due to human error.
So my point here is that if you are trying to add more test coverage and things like this to your code base, but if you actually have to change the code under test to do so, you're adding another element of human error that's probably adding more risk to the project than if you had not done that at all. Now, I'm certainly not for adding more tests. You should certainly do it for new code, but just be careful and kind of thinking about the idea that you want to fix up and get everything to best standards versus focusing on the parts of your code that actually matter. Because when you're adding tests to code you're not going to change, you're kind of being like, let me redo my mouse, sorry. You're kind of being like this guy from Fritz Lang's Metropolis, where, I don't know if you've seen this film, but the opening scene is a bunch of humans slaving and slaving away to just keep some machines running. And so I feel like when you're running a whole bunch of tests, so you have 100% test coverage on code you're never going to change, all you did is be a slave to the computer and make your CI say, hey, nice job, everyone, 100% test coverage. So don't be this guy. And my point is, don't bother changing code if there's not actually a user or business value for doing so. So that cautionary tale aside, let's talk about some strategies how you can incrementally make changes to improve your code base without the same level of risks. So speaking of linting, style guides is something that came up. So at Isotope, many years before this merger, and I'm sure some of you actually, let me poll the room. How many folks deal with code reviews where there are comments about, oh, you didn't follow this part of the style guide? About half the room. That was going on for us too, and we decided that is noise and not the actual kind of feedback we're looking for on pull requests. So we decided if there's rules like this, they should be enforced by machines, not by humans. And there's a tool that comes with clang-format, that can apply formatting rules. It wasn't perfect for our style that we had, but we were able to get it close enough. Now, some people, when they adopt clang-format, will take their entire code base and run clang-format and reformat everything. And yeah, I've heard about that going okay for folks. It might be a little bit annoying with git blame, seeing who did what, but there's ways to work around that. But if you're thinking about a code base like ours, which is essentially a huge number of very small libraries and dependencies, it's not like you're just doing this over one mono repo. It wasn't super practical. And we also wanted to enforce that you couldn't pass your builds if you weren't following the style guide. So we didn't want to make that universal, but we decided, okay, we want to enforce the style guide on any code you change. So one thing is, we always want to provide a clang-format file, and then we wrote Git hooks that would use, that every time you were going to commit code, it would look at the lines. There's actually a tool, clang-format diff, that allows you to run clang-format just on either the staging area or your recent commit or between two commits in Git, and just format the lines that change. It won't be exactly those lines, because if a syntactic construct like a block extends those lines, it will format the whole thing. And we wrote some Git hooks to automatically apply those formattings to changes. And then in CI, we reapply that same diff formatting again to make sure the developers actually have those hooks installed, so that if you didn't actually run the formatting correctly when you committed, the CI will see, oh, you have these formatting mistakes and fail it. And so that's the way we've been able to end all formatting discussions and slowly, incrementally evolve the code base. This is a lot nicer than other approaches which say, oh, use the style of whatever file you're in. Because when you've got millions and millions of lines of code, you're just going to get stuck in your old style forever if you do that. One thing to mention is both with this and the clang-tidy per line stuff I'll talk about later, this has come up in a few talks of mine, and people have been asking about more of the mechanisms about how we got this working because they've gotten stuck. Moving my talk up to today, I didn't get a chance to look up all the flags and hacks we use, but before I publish the slides, there'll be an addendum, which are like the tricks and tips for getting clang-format diff and clang-tidy diff working for you. So the next way to incrementally improve your code base is with static analysis. And people talk about safety a lot these days, even putting like security safety aside, having UB or buffer overflows, et cetera, also just a source of bugs or ghosts that your manual QA can have a hard time tracking down. And again, this is a subject that came up in a talk I gave last year about getting rid of undefined behavior in your code base and legacy assumptions. I'll just, we talk about, the government talks about how scary C++ is sometimes, so you can just enjoy this comment about how scary software is in general. Give you a moment to enjoy that. So anyway, we started working on using and while, yes, these sanitizers now, some of them are available in Visual Studio and GCC as well, our own experience is running these just with Clang. And so we, speaking about that, I'm gonna do is coming from the Apple Clang perspective. So part of why we started being interested in the sanitizers is, in this previous talk I mentioned, at some point we rolled out a guideline internally. You do not write undefined behavior. Because previously there were discussions, oh yeah, this is UB, but I tested it, it works, and we didn't want to go down that road. Especially, this became more important when Apple Silicon came out and we need to start supporting ARM. And so 20 years of Intel assumptions kind of went out the window. So we knew that there were certain threading things, kind of lock-free stuff we were doing that technically worked on Intel according to how the machines work, but didn't work according to C++ language, and was certainly going to be suspect on ARM. So we took a process of trying to roll out address sanitizer and UB sanitizer. And this was a success because we rolled it out incrementally through our code base. More of a failure was rolling out the thread sanitizer for a couple of reasons. One, you have to run it separately than these other sanitizers. Two, we were initially rolling out ASAN and UBSAN on our unit tests, and most of our unit tests weren't doing the gnarly multi-threaded stuff that we knew was going to cause us trouble on ARM. So we didn't take an incremental approach. We set people up to run a thread sanitizer on our full products, log bugs. There were certainly a number of false positives we found, and we needed to figure out how to work around those. People kept filing the same false positives again. And so this was ultimately a long process. And when we finally supported Apple Silicon with our products, we felt very confident that we did it right. But we were slow to market, and we wonder if that we should have maybe taken a more incremental approach there as well, like we did with the other thing. But the most important thing is you could turn on ASAN, UBSAN, and TSAN, but if you don't have test infrastructure and CI to actually exercise your code, you won't get a lot of value for it. So we turn these on, write more and more and more tests for all your new code. And when you're thinking about this, rolling out these sanitizers, it's useful to think about this testing pyramid where you have unit tests where like most of your tests are going to be, they're close to the code, not very brittle. At the opposite end, you have end-to-end testing your entire product. And then in the middle, you might have some sort of level of integration tests. So for us, what this looks like is we have unit tests on any utilities, small functions, low-level DSP algorithms. We then have a way to build DLLs of all of our signal processing algorithms and run them through various regression tests. And then we also have test automation running on the entire plugin that we would deliver to a customer as well. And we're in the process of, we've nailed unit tests at this point. So the last time I gave a talk on having sanitizers everywhere, slowly building the technology to start using the sanitizers in the other areas as well, because we know they're exercising other code paths that unit tests aren't, and they're helping us with bugs. The other thing to think about, this is like a little chart I'll use a couple times. Just imagine this is a code base with a product at the top, some little vocabulary types at the bottom, and various other utilities and libraries you built up to use this. And you don't have to roll out these sanitizers everywhere. Like we started with our lowest level library we called IZBase, got them working there. and then started continuing to build up more and more of our libraries, adding enable sanitizers, fixing any bugs, then continue on to the next library. But we didn't have to do every library before we started using them on a product all the way up top, because even if some of these other orange boxes where we've not enabled sanitizers or fixed all of our UBs, maybe the unit tests in my product up top test these orange libraries in ways different than their unit tests. So it's possible you can actually don't have to go all the way bottom to top, but you can kind of find, oh, I'm stuck in the middle. Hey, let me just try running my tests something higher up, and maybe that will pass. So, but anyway, the point is, take this in small steps. This can seem like a really big challenge dealing with UB in a legacy code base, but it's, can be challenging. And one thing we discovered is we had 2 APIs for kind of registering parameters with our products, like what knobs are on your various guitar pedal simulation or whatever. And at some point, we discovered we had a kind of a modern declarative API for doing this and an old imperative API. And it turned out the old imperative API, which is in most places in our code base, it's a race condition and is UB. It has worked for 20 years. And we'll come back to this later. So what we did is we did not fix that everywhere. We deprecated that API. We know it's broken. When you're in one of those classes, people update it to the new APIs, and you're not allowed to write any more code using that broken API, and that's been good for us. And so later, we'll see how we can deprecate code and prevent people from getting rid of old code, because thinking about all this legacy code, like Gabby said on the security talk on Tuesday evening, it's not like we can just throw all this away. Like there's real customers, real products that need this stuff, and we can't just like pause everything. No customers get everything for 2 years to fix all this. So we have to be real, knowing, yeah, we have this dragon here, and we're not going to feed it anymore, and someday we'll get rid of it. So thinking about changing legacy APIs, like just like getting rid of that ability to have that bad API, or I'll look at a little bit simpler example. We had for probably most of the time in our Boston isotope code base, this thing kind of like a standard optional that we called checked value, but it was super weird. Only worked with default constructible types, had some weird implicit conversions, led to bugs, we realized. So we're like, okay, I can kind of see why the founders wrote that, but let's not use that anymore. So we switched to using boost optional. We felt that was a little bit safer. A little bit later, we're going to be able to adopt standard optional, but we were in a middle ground, so we actually took a transition phase where in some projects we defined in our own project's namespace a optional that was the experimental optional if it existed, or boost optional if not, and then we had to use the kind of subset of APIs that worked for both of those. But my point is, if we then actually getting rid of checked value or boost optional in the entire code base was going to be quite tricky and cause a lot of breaking changes for people. So before I go on that, we can enjoy another comic for a moment. And so one of the dangers of, if I had something like this and I want to say, like, okay, I'm going to release a new version of my library and checked value is gone and replaced by with standard optional. That means all my call sites and clients would have to update their calls to use standard optional instead of our checked value. But what if, and they might say, oh no, that's not so important to me right now. I'll do that update later. I won't get a lot of value out of that. But what if a new version of my library included a change like this? This is hypothetical based on true events. I had a change like this where we say, okay, get rid of checked value. It's standard optional everywhere. Oh, and some of our low-level code that should have been using atomics, we fixed that for Apple Silicon as well. So to support Apple Silicon in your product, you have to take my new version of my library. But I also gave you all these other breaking changes you might not want with that. So in general, I have an attitude of don't make breaking changes. That might sound extreme. And when I've heard that and talked to colleagues, they say, well, how are you going to get rid of old code like your custom capital S string class that you still have or this other stuff? Well, do you have to get rid of that? If it's still working and you don't write a new code, maybe it's fine. But I don't actually mean no breaking changes, there are kind of ways to handle this. One thing is, if you use really small libraries, it's much easier. So if whatever Apple Silicon stuff was somewhere else than where I was changing this checked value stuff, then they could say, oh, I'll take this DSP support and leave this checked value thing on the side. So small libraries, I think, help. But really, I personally have seen success with some teams at Native Instruments with a live ahead approach, where you're not versioning libraries. All your internal libraries, you're always building at the latest version at any point in time. So if I kick off a CI build, I get the latest and latest of everything. And that's a lot of advantages, because I'll know right away when something breaks, and I don't need to look back at months of changes when I'm updating libraries to see what did it. Also, your entire org, or the part of your org that's doing this live ahead, becomes kind of a like instant QA or other sanity check, because if I roll out something that I think is not a breaking change, and then all of a sudden all the teams are like, hey, I can't build, they'll come knocking on my door and say, hey, Roth, you got to revert this code. You broke something. And then we revert it and we do it right later. So I think it actually increases quality as well, this live ahead concept. And whether you're live ahead or not, you do actually want to break stuff sometimes and make changes. And so the best way to do that is in two-stage. Oh, I didn't mention this talk from Titus has a great description of live ahead. It's kind of what got me onto this philosophy and why I don't believe in version numbers anymore. But whether you're live ahead or not, you need to somehow provide ways to refactor code from one to the other, and especially at live ahead, you kind of need to deal with doing two-phase refactorings where you deprecate stuff, provide a new thing, somehow change all the code eventually to use the new thing, and then you can remove the old thing. Titus has a few good examples in here, but the best way to do that is using Clang refactoring tools you can make with clang-tidy to actually say like, oh, everywhere you're using checked value, now use standard optional, but do the extra logic of knowing when we did implicit conversion, what's the smart thing to do here? So I'm still writing that check. But this talk from last year really inspired me to do more of this, because it made it much more accessible. I didn't realize Godbolt can help you with this now. I think I overheard someone telling me that ChatGPT is also really good at writing Clang matchers. So highly encourage that. If you're going to break stuff, think about writing refactoring tools. But live ahead isn't for everyone. Some people need to version components and possibly have multiple versions of components coexist in the same project. So I direct you to this talk from a few years ago from Brett and Daniel at Bloomberg that talks about how they manage packages. And at some point they talk about prime and double prime versions of libraries or other ways of naming them when you're making a change, so you can potentially work with both versions. And so to close off this section on legacy code before I tell my few stories about code sharing, I'm going to talk about static analysis and how we handle those deprecations. So when I said we deprecated our checked value, or we deprecated these UB parameter registration APIs, how do we actually do that to make it so it's impossible to write that in new code? So, and before I get into it, if you've not heard of clang-tidy, clang-tidy is a tool that comes with Clang, performs a bunch of checks, some related to core guidelines, like, hey, making sure you're following rule of 0, rule of 5, not putting static in headers, You can make your own rules. So like we've made certain rules about some of the checked value APIs that are really bad. There's a rule we have against that. One of the downsides of making your own custom rules, you have to build your own copy of Clang to do that. There's no like kind of plugin system for that. And the way we approach this is we use clang-tidy diff, similar to what we're doing with clang-format, where again, we're only going to, obviously clang-tidy will still need to compile the whole file, but it will only report the warnings and errors on the lines that you care about from your diff. And so this way, again, we can enforce our rules on any new code people write, but the tools aren't going to make it so, I opened a PR with this class where I added one new method and followed all the rules, but it didn't do rule of 5, so now my build fails because somebody else didn't do rule of 5. Only your changes will fail the clang-tidy tests in our CI, so that we're only worrying about improving the new code. We don't have to force ourselves to go back and fix everything. Occasionally we do run it on a whole project with the fix-it flag and fix a bunch of stuff, but in general, we're focused on new code. There's a few things you might need to do to get this work. You have to make a Clang compilation database. If you use precompiled headers, you might need to edit the database to put back in the real header. We found on Mac, Clang will try to compile, clang-tidy will try to think a header is always a C header if it's .h, so we force it to think those are Objective-C++. And here's the trick about how we deal with the deprecation. So normally in our builds, we have most errors as warnings, but some not. And so deprecations in a normal build are just a warning. But when we run clang-tidy, we set deprecations warnings as errors. So if you use deprecated code on any line you change, you'll get an error. And this actually can be used for rolling out other warnings as errors. Like for example, if there's a warning as error that you know would be great in your code base, but you violate it everywhere, leave it as a warning in your normal builds, but switch it to a warning as error when you're doing this clang-tidy diff, and then you'll only kind of not be allowed to verify that warning any further. Again, we verify this in CI, and the other tip is have an easy way to disable this in CI. Because when you add a deprecation attribute to some class, clang-tidy will fail that as an error for using deprecation. So you usually have to go through the stage of deprecate something and turn off the clang-tidy. And then once that's landed, future clang-tidy runs will see that thing as deprecated. And again, I'll put an addendum in the slides before I publish them with a little more details on some of the flags we use to get this work, but I didn't get a chance to pull them out ahead of time. And you may ask, well, if we're deprecating all this stuff and not deleting it, like, aren't we just gonna just have all this bloat that grows and grows and grows forever? Well, no, because people hate this old garbage code and they want to get rid of it. And we'll see over time as more and more new code is written using non-deprecated functions. When you're editing code that uses a deprecated function, you'll tell your build and that will force you to switch to the new functions. And eventually over time, you will have less and less and less of this stuff in your code base. And eventually you can realize, oh, I can actually refactor a few things and pull out and kill this deprecated thing. So part of how we motivate people, not just letting stuff rot, but actually getting rid of stuff from the code base when we've actually fully moved away from it, is in our Slack, we have a channel called the Red Diff Appreciation Society, where we brag to each other about pull requests that only delete code. It's super fun. I recommend it for everybody. One of my favorite releases where just people like to nerd out on stats, I did like, oh, lines of code changed in this release. And I think we deleted twice as much code as we wrote in that release while adding a lot of features, which was super fun. Okay, so that's kind of some tips and some stuff from previous talks on how I've dealt with legacy code. But now let's quickly breeze through a few code sharing strategies I've had for sharing legacy code, and then we can get to some questions. So I'll kind of go through this a bit quick because we're low on time because I started late. So one thing that comes up when we went through this merger is this desire to standardize and share stuff right away. More for management than the engineers, but the engineers were a little bit interested also. For example, we have lots of similar DSP algorithms across the companies, like basic filters, et cetera, generating noise. We also have a lot of very unique proprietary DSP algorithms that now that we're one company, we'd love to share with each other. I think if I counted, including our now use of embedding HTML web views, we might have 7 in-house and some external like Juice and Qt UI libraries in play in various places. That's definitely something we want to look at addressing. We have 4 text installer technologies. You know, we could go on and on. So another comic time about standards. Now, I think this is actually not the problem you'll have at a company. Likely, we wouldn't make a 8th UI library, or a 5th installer technology. Likely, we would say, like, okay, what's the one that's closest to serving everyone's needs? How can we add a few other features so that one could be the standard? Well, some people in this room might have some experience with the ISO C++ standard and knows how many years that process of making the one thing that will work for everybody can take. And so, like, we can't spend all our time standardizing UI libraries. Even if we have the one that works for everyone or the one installer, the cost to then bring that installer across 10 products is significant. And that time could be spent delivering value to the users, which is money to the business. The other thing that came up is like, oh, again, we have our like code base. And imagine if it wasn't just all our code, but what if we had like, you know, these orange and green could be Isotope and Native Instruments code. And then what if we sprinkled in some Brainworks code in here? This sounds really cool. We're sharing all our cool Lego pieces. But, well, see, there's that like lonely Brainworks purple in the bottom, depending on Isotope orange stuff. Like, how's that going to work? So the idea that you can like take little bits out of these legacy code bases and just slot them together It's not going to work out of the box. So diving into actually standardizing, I think you should take it slow. But what is worth doing is discover your hidden gems. So you should get together engineering, architectural leaders, and discuss, show off the cool code that you're proud of. Hey, we got this library. It works really nice for this reason. We wrote it because we had this other thing we didn't like, and show a code you don't like. So everyone knows, like, oh, one of the companies actually is like needing maybe new UI solutions. So they know now, oh, what maybe we could draw upon on the future. And the other technique I'd recommend is this thing a colleague showed me called a tech radar. There's a link to read more about this, but essentially for technologies or processes or tools or languages, you kind of want to categorize them into different categories of like, this is something we're exploring using. This is something that's like on ice and we shouldn't use this in new code. This one's a standard practice. So kind of everyone in the organization can understand the palette of technology you have and when you should adopt one and when, oh, this is old, don't use this in new code. So in the last few minutes, I'll breeze through my kind of couple code sharing technique stories, but audience participation time real quick again. Does anyone have any guesses of challenges that might come up in sharing 20 plus year old C++ code bases with other, not just one other, but two other ones of those?
Dependency hell.
Yep. Dependency L. Standard differences. Different compilers. Luckily, we didn't have versions yet. No, luckily, not too many different compilers for us. Engineer that never learned how to use templates. Luckily for us, I give tons of internal talks on templates because it's a fun topic of mine. So I'll move on to a couple of things that I brought up. Yeah, different build systems, different language standards, different versions of third-party libraries, precompiled headers that you might rely on. And the danger there is if you have a precompiled header, that could mean that you're accidentally writing header files that don't include everything they actually require because your precompiled header that's included before your other headers gives you that stuff. So, they can cause you some trouble. Weird legacy vocabulary types. If you don't know what I mean by vocabulary type, that's, kind of basic types like things like optional or span, kind of, things that allow you to kind of use your bytes in kind of specific use cases. Global namespace. We have a bunch of stuff we put in the global namespace in our precompiled header that probably seemed convenient 20 years ago, and yeah, it was stupid, sorry. Different error handling strategies and different coding styles. So on the coding styles, please provide, if you don't use any tooling, don't automatically do it, please provide some clang-format file in your code base if you're dealing with a large company, especially merged companies, so that if someone's working for you from another team, they don't have to learn your style guide. They can just have the machines do it for them. So the first one we're going to quickly look at is dynamic library sharing. The idea here was very early in the merger. Up top is Ozone, our mastering software, and we want to take the mastering limiter for that. If you know what that is, it basically is a feature at the end of your mastering signal that makes it loud. And we want to put it into our DJ software, Tractor. And so I was thinking about how to do that, and well, luckily we kind of had a system already set up for this. We had something we called testable DSP, where every DSP algorithm we make a dynamic library, and we have a test harness. It does various things. Like in this case, the kind of bluish and orange examples are maybe a new build and a gold build that we know the orange is like good behavior. We set parameters on both of them. We run the same audio through both of them and see, are the results the same within some tolerances? This is also very common in medical imaging and really any kind of other things like this. We also might just run the same processor against itself to make sure it's deterministic. That's a very simple API. We have some C functions that are exposed from the DLL to create these processors. This is very simplified, but the processor has a simple API, pure virtual, for setting parameters, resetting it, processing audio. And one thing I want to point out, people sometimes think dealing with a DLL and DL open and DL sim that you're stuck with just C functions, but you can have a C function that creates a pure virtual interface that you can pass between DLLs. This is a normal move, certainly in Mach-O and Windows builds. I believe this also does work on Linux as well. And the one thing I'd recommend keeping in mind is I tend to stick just to primitive types, but also you probably also want trivial types in these as well. I think you can get into some ABI, who's deleting what memory weirdness if you're dealing with other types in this. But the really cool part about dynamic library sharing is it creates this wall. And all of my daemons from my legacy code, my capital S string, my version of Boost, all the stuff I put in the global namespace, precompiled header can stay over here, and your Boost and your stuff can stay over here. And we don't have to worry about the ODR and other stuff as much if you're using dynamic libraries, and specifically not like using weak symbols, but if you load dlopen or dlsim and the Windows equivalents that kind of make a nice firewall. And this works so successfully, this is now a standard way we share DSP, where element is an isotope style DSP, we wrap and tessel the DSP, and now we have an adapter turned to an IDSP core that the folks in Berlin can use. And we're building other wrappers going the same way. And one thing to keep in mind, if you do this, thinking about running UBSAN, you also will want to expose these virtual interfaces that you share across the DLL boundary. Expose those symbols, like so on Mac with attribute visibility default, DLL export on Windows. And so the reason for this is the type info, if you don't do this, the type info will be different between this class in the DLL and outside the DLL. And even though they are the same type, the way that UBSAN detects that you're using pointers of the same type will think they're not. So if you want UBSAN to work across DLL boundaries, you have to do that. The holy grail of this is source code sharing. We had some success with this. Some header-only machine learning stuff was really easy to pull out. We shared an auth library by splitting it out of the monolithic library, changed custom vocab types to standard types, agreed on third-party libraries, like, oh, we use Boost, base64, and Lomon JSON, and we were like, oh, we don't use base64 and Lomon JSON yet, but they're better than what we are using, so sure, we'll take them and use them in new code. Then you write build scripts for both, and that does work to share source code on small scales where you don't have many dependencies on your other stuff you don't want to share. Another option is copy and paste sharing, which might sound silly, like don't repeat yourself, but actually can work pretty well. So we have this distortion product called Trash. There's actually a new version of it out. And our guitar pedal and amp simulator guitar rig has this new module called Color. They wanted to include some of the distortions from Trash, and they looked at the code, and some of them were very simple, pure functions, essentially a transfer function, one float in, one float out, a couple lines of code. Others were more complex, but any of the simple transfer functions, we didn't need to like figure out a library to share. They just copy and paste them. And that totally worked. Did your slide get out of order here? Well, we might come back to a slide on that, but essentially, there's another slide here somewhere that says, this worked really well when, these little functions will never change. We also did some copy paste sharing on some like ways the plugins share data betweenplists and registry keys, between products, between native instruments and isotope. And we thought that code would never change, but next week when I get back, I need to investigate why now the outputs drift. And so clearly, someone in Berlin made a change there, and we didn't know we had to copy and paste that change. So if it's small and no change, copy paste can be good, but it comes with risk. Now here's maybe the crazy one, static library sharing. Okay, I hope you all haven't think I've completely lost my mind, but this is probably the worst technique, but it works. So we had a usage analytics library. Don't worry, we're protecting people's privacy, the GDPR in California rules, you have to opt into all of this, but it does help us understand and make our products better. So we had this library at Isotope, and Native Instruments had theirs, and Brainworks did not have something like this yet. So we wanted to share our library with them. And had different layers, and they decided, oh, the reactive programming layer to dispatch events that you guys have, that'll be too hard to integrate, but we like all your lower level stuff. That will save us a lot of time. So we're like, okay, let's integrate that. So we looked at source code sharing, and unfortunately, this depends on like seeing the opt-in and other things on this class we have called util config file. It deals with plists and registries on Windows. It heavily uses our capital S string, which is our old string, and like it's a lot of code to refactor that before we can pull it out. We're working on it, but that'll take some time. But okay, we know dynamic library sharing works. We can just decide a abstract interface for that teal box on the bottom, and we're good to go. But unfortunately, Brainworks installer tech would have required an investment to install this additional dynamic library with the products. And since our long-term goal was source sharing this library, we felt, well, do we want to actually invest in temporarily installing DLLs? So we decided, hey, we'll just build you a bunch of static libraries of the analytics library and all the third-party libraries it uses, and you can just link those in your project. How many hands think that worked the first time we tried to do that? None. Good. Yeah, it didn't. So we had to figure out, we had to negotiate some flags. We got to get our flags in order. So I don't know exactly why we had to add the queue unused arguments flag for macOS, but there was something, I think there was a flag we were passing that they were on a slightly older version of Apple Clang. So I think we were passing a flag that they didn't like. So we added that. And then this no Objective-C message send selector stubs. This is an optimization that later Apple Clangs do for Objective-C code, and their old Xcode wasn't compatible with that, so we had to pass that flag to make it work. On Windows, you got to agree on iterator debug levels, static or dynamic runtime. We had to enable the multi-threaded DLL. I don't know what that means, but I had to turn that on at some point. It's like runtime version 3 instead of 1 or something. And a lot of other flag dances where we went back and forth turning on different flags we thought were the problem. And the way we delivered this is we built a dynamic library essentially to like cause the static libraries to be built. I turned off LTO for paranoia, maybe doesn't matter. And it worked and is in production. And you might think, oh God, is this horrible thing gonna stay in production forever? No, because my colleagues in Langenfeld do not like this. They wanna move away from it. We have scheduled engineering investments to try to actually move to source level sharing. But it allowed us to ship these updates a lot faster than if we actually split out the library properly for source level sharing. So to sum up, focus on improving new code. You can't fix everything and you can't throw it away. Incrementally adopt clang-format, incrementally adopt sanitizers, incrementally adopt clang-tidy, and your code will get better and better. Thank you very much.